All right, this is the Chapter 24 Extra Edition. Number 3 in the problem set asks you to draw the cyclic hemiacetal that's formed when each of the bifunctional compounds is treated with aqueous acid. So we're making the hemiacetal, and it's going to be an intramolecular one. The alcohol here is going to attack this carbon, and that oxygen is going to be part of the ring. So the number of carbons or atoms in the ring will be 1. We'll have a 5-membered ring. That becomes an alcohol. At 4, we have 2 methyl groups. 5 is the oxygen. And the new bond is formed between carbon 1 and the oxygen. So that would be the hemiacetal that we formed there. In B, we'll have a 6-membered ring. Here our dimethyl is at 5. And I have an oxygen coming off of 5. And a new bond to the oxygen. So that's the hemiacetal that we formed there. Here we have a 7-membered ring. And our alcohol there. So that's how we would figure out the hemiacetal. All right, question number 5 is asking us to draw a Haworth projection for each. So we're looking for the alpha, which means that our O is down. And remember, all the groups on the right side are down, left side is up. So all of our things should be down. We have 1, 2, 3, 4, 5, 6 carbons. So I will have a 6-membered ring. Our OH is down because it's alpha. And then everything else around the ring was also down. All right, so that's how you do this one. For beta mannopyranose, our alcohol is going to be up. So at the anomeric carbon, which is carbon 1, CH2OH, this is 2. All right, at 2, our alcohol is on the left, so this should be up. At 3, it is up. 4 is going to be down. So that's how we do that. The trick here is remembering which order to number in the Fisher projection. 1 is always at the top or at the aldehyde. And then when you number here, the hemiacetal is 1. The oxygen is going to be coming off of carbon number 5. So just number 1 on this side and then go around clockwise. Number 8, draw the product obtained when each is treated with acetic anhydride in the presence of pyridine. So this is our acetic anhydride. This is the structure of galactose, so we can put that into the pyranose form because we're reacting it with the pyranose. You can do it in the chair or you don't have to. Let's just do it not in the chair. Alpha is down. All right, at 1 is this one. 2 is down because it's on the right. 3 is up. 4 is up. So when we react it with acetic anhydride, all of that is going to get acetylated. Including the alcohol up here. And we'll see the same thing with the glucopyranose. And I'm just going to draw the product of this one here. So our alpha would be OAC. This one is 2. have down OAC. This is up OAC, and 4 is down. So that's what that one would look like. Here we are going to draw the products formed when the aldopentoses, this one here, undergoes a Kiliani-Fisher chain lengthening process. So we're using the HCN, H2 palladium, barium sulfate, and water. So this is here before. We're going to get that alcohol. This is the new aldehyde. And then we'll form another new aldehyde with the epimer, where the OH is on the other side. But all the other ones stay the same. All right, so that's the Kiliani-Fisher synthesis. In this reaction, predict the product that's obtained when cell bios is treated with each of the following. So this is the structure of cellobios. With sodium borohydride, this exists in equilibrium as the aldehyde, so this will get reduced. All right, so this one exists as the aldehyde, such as that. So when we reduce it with sodium borohydride, we should get the alcohol there. All right, so that is where it got reduced. For bromine and acetic acid, I'm going to call this whole group here R. That's going to oxidize that carbon. To the carboxylic acid. That becomes the alcohol. So that's what that one would look like. Methanol is going to convert just the acetyl carbon to the methoxy. And then for the D, all of those will get acetylated. So those are the reactions that you would do with a disaccharide. Okay, draw the open form of each. So we're going to start with our open aldehyde. Probably have 4 carbons in between. This would be the D, but you could have the L as well because it could form either. At 2, that's down, so this should be on the right. 3 is down. 4 is down. So that's how you do that one. This one is the same process. Two is down. Ooh, except at the top here we should have a CHO, CH3. All right, and then this one is up. And that one's down. And we can make it the D. All right, when D-galactose is heated in the presence of nitric acid, an optically inactive compound is obtained. Draw the structure and explain. So this gets oxidized to the carboxylic acid. So does this one. And previously it was chiral because the aldehyde was at the top, but now we have carboxylic acids at both ends. We have symmetry, so that is no longer chiral. So it's optically inactive. All right, here we're going to do our reactions. Sodium borohydride. We're going to get the alcohol at the top. That one's up at 2. 3 is down. 4 is up. And 5 is just, we'll just use the D. For the Br2, that's going to oxidize the top one. Everything else stays the same. Nitric acid, we're going to oxidize both. For methyl iodide, we can leave that in the cyclic form. That one's going to methylate all the alcohols. Methanol will just do the hemiacetal. Keeleani is going to add a carbon. And then with the wall degradation, we're going to lose a carbon. And there is your extra edition of chapter 24.